In early 1943, as combat operations across the European and Mediterranean theaters demanded increasing precision and reliability from the air forces, American command paid particular attention to the condition of its fighter units. Among the aircraft heavily involved in escort missions and aerial interceptions, the P-38 Lightning held a special place. This twin-engine fighter offered high speed, strong armament, and stable performance at high altitude. Yet despite its advantages, the aircraft had several operational vulnerabilities that became especially noticeable under field conditions. One of the units actively flying the P-38 was stationed at an airfield in the Mediterranean theater. The base was located not far from the front line, and aircraft took off several times a day, escorting transport planes and bombers. Under such heavy operational tempo, constant flights between bases, and irregular supply lines, the technical crews faced numerous small malfunctions requiring quick field solutions. According to maintenance logs, the most troublesome area involved the cooling system and the manifold pressure control, both of which relied on stable wiring routed along the aircraft's fuselage. For several weeks, different crews reported intermittent electrical disruptions. These disruptions did not directly cause accidents, but they posed a serious risk in combat, as they could destabilize engine temperature control or interfere with essential instruments. The issue appeared inconsistently. For some aircraft, it occurred during takeoff. For others, in mid-air or during a sharp climb. The root cause was unclear. The most likely explanation pointed to micro-damage in wiring hidden inside narrow channels of the airframe. The P-38's complex internal layout made thorough inspections difficult, especially during rapid turnarounds between missions. Observations showed that high-G maneuvers might cause certain wiring segments to shift or stretch slightly. Command forwarded the issue to the engineering staff, who began a detailed analysis of the aircraft's structural features. At the same time, flight reports were reviewed. Pilots noted that disruptions often occurred during rapid altitude changes or sudden acceleration. This pattern suggested that structural stress during these moments caused small shifts in wiring sections insufficiently secured within the fuselage. Still, there was no direct physical evidence, and inspecting every aircraft was time-consuming. Under wartime conditions, with high mission frequency, deep diagnostics were often conducted under pressure. Faced with these constraints, the engineering teams were forced to consider unconventional solutions. Various reinforcement ideas were proposed, but most required removing fuselage panels or disassembling internal structures, tasks impractical without grounding aircraft for extended periods. Although the issue had not yet reached a critical stage, records indicated a gradual deterioration that could escalate into a serious failure. During one of the routine maintenance checks, a mechanic noticed that a section of wiring near the aft fuselage vibrated slightly when the engine idled. The vibration was small, but enough to cause continuous rubbing against a metal surface. Upon closer inspection, small traces of insulation wear were found, minor yet significant signs that under higher loads, they could become dangerous. This confirmed that dynamic stress during maneuvers was indeed transmitted through the aircraft's structure and affecting the wiring. With limited time and a shortage of proper replacement clamps or brackets, the ground crew searched for the simplest possible stabilizing method. Traditional approaches required time they did not have. What they needed was a field-expedient solution, something that could secure the wiring without extensive disassembly. Several ideas were considered, but none provided both speed and reliability. It was in this setting that an unusual idea emerged, one that initially caused skepticism among the technicians. The solution was so simple that it was dismissed as a temporary patch rather than a viable fix for combat aircraft. Still, given the constraints and the growing urgency, it became the only feasible option. At that moment, no one suspected that this improvised measure would later prove decisive in preventing a much larger disaster. As maintenance efforts continued, engineers monitored the aircraft fleet closely, recording each irregularity in order to establish patterns across multiple P-38 seconds. Over time, the notes revealed small but significant correlations between structural stress and electrical behavior. Aircraft assigned to high-altitude escort missions experienced more disruptions than those performing shorter patrols. The cumulative data suggested that vibration and flexing of the airframe during extended operations were key factors. The improvised wire stabilizing measure, though initially considered only a temporary patch, began to show measurable benefits. Technicians applied it selectively to aircraft with the most frequent issues, documenting changes in performance. In several cases, the intermittent disruptions ceased entirely. Still, there was hesitation to adopt the method widely, as many regarded it as too unrefined for long-term use. The engineering section preferred to rely on standardized procedures, and the improvised solution appeared too simple to earn immediate acceptance. Despite this skepticism, field conditions demanded practical results rather than theoretical approval. Aircraft turnover between missions was high, and resources were stretched thin. The unit received intermittent shipments of parts, but not enough to carry out comprehensive electrical refurbishments. As a result, the staff relied increasingly on whatever functional methods were available. Reports sent to command described the stopgap technique as operationally effective but unconventional, highlighting that it addressed symptoms without solving underlying design limitations. During this period, the squadron entered a phase of intensified operations. Intelligence indicated increased enemy air activity near critical supply routes. P-38 seconds were tasked with long-range patrols to deter hostile interceptors and support transport corridors. These missions placed additional strain on the aircraft, pushing engines and systems to their limits. As the tempo increased, the importance of stable instrumentation became even more apparent. Any electrical failure risked misreading temperatures or fuel levels during high-altitude operations, potentially endangering the entire mission. Maintenance logs recorded fewer failures among the aircraft fitted with the improvised fix. Although not officially recognized, the wire stabilization method demonstrated reliability in conditions far harsher than it had been designed for. Engineers continued to refine the approach, adjusting the tension and positioning to account for variations between individual aircraft. Over time, it became evident that the simplicity of the solution was one of its strengths. It could be applied quickly, did not require special materials, and allowed aircraft to remain mission-ready without prolonged downtime. Meanwhile, intelligence teams tracked enemy movements and reported signs of a buildup near a key coastal convoy route. The squadron received orders to prepare for extended operations over this area, as the upcoming resupply mission was considered strategically significant. The P-38 seconds were expected to maintain air cover throughout the operation, leaving little margin for mechanical failures. Command emphasized reliability and instructed ground crews to minimize risk wherever possible. This directive prompted a reassessment of maintenance priorities. Although traditional methods remained preferred, the improvised wire technique was increasingly viewed as a practical necessity. With limited personnel and the expectation of continuous sorties, the engineering staff implemented the measure in a broader capacity. The decision was framed not as an endorsement of the method's ingenuity, but as a precaution aligned with operational demands. As preparations for the convoy escort intensified, the squadron underwent a final series of tests. Aircraft systems were run at varied power settings to detect any lingering inconsistencies. Those without the stabilizing fix exhibited minor but notable fluctuations, while the modified aircraft displayed greater stability. This reinforced the belief that the simple wire measure provided a meaningful improvement under field conditions. Communication from higher command mentioned the possibility of encountering well-coordinated enemy aerial resistance. The P-38 seconds would play a central role in maintaining air superiority over the convoy route. With the prospect of sustained operations and limited support infrastructure in the region, every technical advantage mattered. By the time the squadron received its launch orders, nearly all aircraft had been equipped with the improvised fix. Although originally dismissed as insignificant, it had become an essential measure contributing to readiness. The crews, engineers, and pilots understood that the true test of the solution would occur not on the ground, but under operational pressure in the skies ahead. Unbeknownst to them, the upcoming mission would reveal the full significance of the simple wire that quietly reinforced the squadron's reliability. In the days leading up to the convoy operation, weather patterns shifted unpredictably across the Mediterranean region. High-altitude winds fluctuated in strength, and dense cloud formations occasionally forced reconnaissance units to adjust their routes. The squadron received updated operational briefs outlining potential visibility challenges during the upcoming mission. These environmental factors placed additional stress on navigation instruments and engine management systems, heightening the importance of stable electrical performance. Ground crews conducted accelerated inspections under increasing time pressure. Aircraft were aligned in rows along the airstrip, and each underwent essential checks related to fuel flow, engine temperature regulation, and electrical diagnostics. Observers noted that the aircraft equipped with the improvised wire stabilization demonstrated smoother readings during engine warm-up cycles. The modification, though still unofficial, became integrated into the pre-flight routine as an accepted component of field readiness. As the scheduled mission approached, intelligence units detected signs of enemy interceptor activity concentrated near the convoy's expected route. The reports suggested the possibility of coordinated attacks designed to disrupt supply lines. P-38 seconds were assigned multiple layers of responsibility: high-altitude coverage, mid-level interception, and rapid response maneuvering as needed. These requirements underscored the risks involved. Failures in engine temperature monitoring or momentary electrical instability could compromise formation integrity or force premature withdrawal. Pilots reviewed mission plans in the operations tent, studying altitude profiles, fuel consumption estimates, and rendezvous points. Although the improvised fix had not yet been formally documented in official manuals, pilots were aware of its presence and the preventative role it played. Field experience showed that the technique significantly reduced unexpected system fluctuations. Even without detailed technical understanding, pilots recognized that greater stability meant fewer distractions during combat. On the eve of the mission, atmospheric conditions worsened. Strong crosswinds swept across the runway, carrying dust and debris. Maintenance teams worked through the night to reinforce vulnerable areas on the aircraft. They rechecked control surfaces, secured access panels, and verified the integrity of fuel lines. With limited artificial lighting, the crews relied on portable lamps to illuminate the narrow interior sections of the fuselage. In these conditions, the wire fix proved especially valuable, allowing technicians to stabilize wiring quickly without removing structural components. When dawn arrived, the convoy operation commenced. The P-38 squadron lifted off in staggered intervals, climbing into layered cloud formations. Radio transmissions indicated turbulent air at higher altitudes, forcing some aircraft to adjust their climb profiles. Despite the variable conditions, instrumentation remained stable across most of the fleet. Pilots reported consistent temperature readings and no electrical disruptions during the ascent phase. The early stage of the mission proceeded without irregularities. Upon reaching the patrol sector, the P-38 seconds established their designated formation above the convoy route. Below, transport vessels advanced steadily across open water, maintaining strict defensive patterns. The airspace remained calm during the initial hours, though scattered radar signals hinted at possible enemy activity further inland. The squadron maintained a rotating coverage cycle, with aircraft periodically repositioning to compensate for visibility changes caused by drifting cloud layers. Midway through the operation, radio monitors detected signs of hostile aircraft approaching from higher altitude. The squadron adjusted its formation to intercept. P-38 seconds initiated controlled climbs to gain positional advantage. During these maneuvers, electrical systems experienced significant load fluctuations due to engine power adjustments and rapid environmental shifts. These were precisely the conditions that had caused intermittent system instability in previous months. Yet now, aircraft equipped with the improvised stabilizing fix displayed uninterrupted instrument performance. Their readings remained consistent even during steep climbs. The enemy formation eventually appeared on the horizon. A group of fighters descending toward the convoy corridor. The P-38 seconds advanced to intercept, relying heavily on engine output regulation to coordinate timing and altitude. Stability of the instrumentation was critical during these moments. Any deviation in temperature readings or electrical feeds could disrupt the integrity of the formation. However, telemetry logs later showed no anomalies in the aircraft fitted with the field modification. The engagement developed quickly. The squadron maneuvered to block the enemy approach, maintaining well-organized altitude separation. Environmental turbulence continued to increase, placing further mechanical strain on the aircraft. Even under these conditions, the electrical systems in the modified aircraft remained stable. Ground crews would later confirm that the improvised wire technique played an essential role in preventing short-duration fluctuations that previously appeared during high-stress maneuvers. As the first phase of the encounter progressed, the P-38 seconds maintained a tactical advantage. The convoy remained unthreatened, and the squadron upheld cohesive operational structure. The events that followed would demonstrate just how critical the seemingly insignificant modification had become and how its impact extended far beyond the expectations of those who first implemented it. As the aerial engagement intensified, the squadron faced rapidly shifting conditions. Enemy aircraft attempted successive approaches from varying altitudes, forcing the P-38 seconds to perform repeated acceleration cycles, sharp turns, and altitude changes. These maneuvers placed heavy demand on both engines and electrical systems. Historical records confirm that under such circumstances, even minor fluctuations in engine temperature readings could influence pilot decisions, potentially impacting the defensive integrity of the formation. During these high-stress maneuvers, the practical value of the improvised wire fix became increasingly evident. Aircraft equipped with the modification maintained consistent electrical performance, allowing pilots to sustain focus on tactical priorities rather than troubleshooting instrument instability. In contrast, a small number of unmodified aircraft showed minor but noticeable variations in several readings, reinforcing the conclusion that the earlier intermittent disruptions had not been random but structural in nature. The engagement lasted significantly longer than anticipated. Enemy fighters executed several probing attacks, attempting to draw P-38 seconds away from the convoy. The squadron maintained its defensive grid, adjusting spacing to counter these movements. Throughout these adjustments, engine monitoring remained stable in every aircraft fitted with the wire fix. The reduced workload on pilots directly contributed to maintaining formation discipline during complex maneuvers. As the enemy's efforts intensified, atmospheric turbulence increased. Strong updrafts and crosswinds swept through the combat area, creating additional stresses in aircraft frames and internal wiring channels. Under ordinary circumstances, such conditions could have triggered intermittent electrical irregularities. Logs from previous missions documented instances where rapid altitude shifts had caused transient disruptions. This time, however, the modified aircraft continued to operate normally. According to later engineering assessments, the wire stabilization significantly reduced micro-movements within the fuselage that had previously affected wiring integrity. Eventually, after prolonged engagement, enemy aircraft began to withdraw. Reconnaissance later suggested that they had exhausted their fuel reserves and were unable to maintain sustained operations over open water. The P-38 seconds held their protective positions until the threat fully receded. With the immediate danger gone, the squadron transitioned into a monitoring pattern, escorting the convoy through the remainder of its route. No further hostile activity was detected during the final phase of the mission. When the aircraft returned to the airfield, maintenance teams performed accelerated post-mission inspections. Engine data from the onboard instruments was reviewed, along with structural assessments of frequently stressed areas. Technicians observed that electrical system performance in the modified P-38 seconds had remained stable throughout the engagement. Subsequent analysis indicated that the improvised method had effectively mitigated the wiring displacement that previously caused intermittent disruptions. The significance of this outcome gradually became clear as the collected mission records were reviewed. The improvised wire technique, initially regarded as a temporary and almost trivial measure, had contributed directly to the operational stability of the entire squadron during one of its most demanding missions. The aircraft that relied on the modification reported no electrical irregularities, enabling consistent coordination and reducing pilot workload during a complex aerial defense. Although the method never received formal recognition in standardized manuals, it became a reference point within the unit's internal maintenance documentation. Ground crews adopted it as a practical field solution whenever supply shortages prevented more extensive repairs. Its simplicity proved to be its greatest strength, offering a rapid and effective measure against a recurring structural issue. Over time, the significance of the convoy escort mission was noted in squadron records not only for its tactical success but also for the demonstration of how an improvised technique could enhance operational readiness. The simple wire stabilization, once met with skepticism, became a quiet example of how field ingenuity could impact mission outcomes far more than initially assumed. The surviving documents highlight an essential theme common throughout wartime aviation. Complex problems often require unconventional solutions, and even the smallest adjustment can influence the course of an operation. In this case, a measure that appeared insignificant at first glance played a crucial role in ensuring the stability and performance of the P-38 seconds during a critical engagement, effectively supporting the squadron when reliable instrumentation mattered most.